Welcome all of you to the video lecture series on fluid mechanics. This lecture is on topic 4 on mass conservation and Bernoulli's equation. The title of this lecture 14 is on Bernoulli's equation, which corresponds to the section 4.2 of the topic. Bernoulli's equation is obtained from the law of conservation of mechanical energy, where we consider that mechanical energy can neither be created nor be destroyed, and it gets converted from one form to the other. And in this class of mechanical energy, we basically consider three energies: flow energy, which corresponds to PdV type of pressure into change in the volume type of energy, then kinetic energy and potential energy. When we talk about this law of conservation of mechanical energy, we take situations where the compressibility effects as well as the frictional effects, the viscosity based frictional effects are negligible. Although this equation is quite restrictive as far as the assumptions that are being used, however, for many fluid flow situations, it is widely used as a powerful tool as it gives us certain limiting values for various engineering applications. The learning outcomes for this topic on Bernoulli's equation is, after you go through this topic, you will learn to recognize various forms of mechanical energy. As I mentioned earlier, the various forms of mechanical energy are flow energy, kinetic energy, and potential energy. It is expected that you will understand the use and limitations of Bernoulli's equation. And finally, through this topic, you should be able to apply Bernoulli's equation to solve a variety of fluid flow problems. I'll have a separate tutorial video lecture on problem solution where I'll present 3 different problems where you will learn to apply Bernoulli's equation for certain engineering problems. Let us start with an introduction to Bernoulli's equation. It's an approximate relation between pressure, velocity, and elevation in a fluid flow situation, and is valid during steady flow when compressibility and frictional effects are negligible. This is basically applicable for incompressible and inviscid flow regions. It is based on law of conservation of mechanical energy for systems that do not involve any conversion of mechanical energy to thermal energy. What is considered mechanical energy is basically the 3 energies corresponding to pressure, the flow energy corresponding to velocity, we have energy which is called as kinetic energy, and corresponding to the elevation, we have energy which we call as potential energy. So this mechanical energy consists of flow energy, kinetic energy, and potential energy. And when we talk of the Bernoulli's equation, it involves the law of conservation or the summation of these 3 energy, where any of this mechanical energy is not getting converted into heat such as thermal energy, and neither the transfer of heat is leading to change in this mechanical energy. This equation is quite simple, and despite its simplicity, it has proven to be a very powerful tool in fluid mechanics. The Bernoulli equation is not applicable everywhere in the flow. Just to give an example, if you consider this problem corresponding to free stream flow, external flow over aerofoil, this is an aerofoil with certain angle of attack, then what you see is that when the fluid passes over this aerofoil, there is a growth of a boundary layer over the surface of the foil, and on the back side there is a flow separation, and the velocity of the fluid on the back side, there is a recirculating region due to the flow separation. This is called as wake. So above the aerofoil you have a boundary layer, and on the back side you have a separated region which is called as wake. So in this separated region and inside this boundary layer, the velocity gradients are large. Note that this aerofoil is stationary and the fluid has a certain velocity. So when it passes over the surface of the stationary, there is a velocity gradient which sets in, because at the solid surface you have a no-slip boundary condition. So inside the boundary layer, the velocity gradients are large, and what whichever fluid you consider, it has certain uh, viscosity, and due to which there will be viscous resistance. So inside this boundary layer and on the backside where you have a separated flow region which is called as wake, the viscous effects are large. So in this region, which is shown by gray color here, Bernoulli's equation is not valid. So in the region where viscous effects are considerable, the Bernoulli's equation is not valid. Away from this region, that is the boundary layer and the wake region, as you go far away, in this region, although the fluid has certain viscosity, but the velocity gradients are small enough and such that the effect of viscosity is negligible. So in this region, we call as inviscid flow region. In this region, the Bernoulli's equation is applicable. The Bernoulli's equation is applicable for steady flow, inviscid flow, and incompressible flow. So as mentioned, the applicable in inviscid regions of the flow, region outside the boundary layer and wakes. And as I mentioned, the viscous or the frictional effect. When I say friction, what I mean is that any fluid has certain thermophysical property, which is called as stickiness. The stickiness between the different layers of the fluid resists the relative motion between the different layers of fluid. It's a fluid resistance which causes the decrease in the relative velocity between the different layers of the fluid. It causes certain frictional effects. So these viscous effects are considerable or appreciable close to a wall, such as the wall of the aerofoil in this case. And that close to the wall, we have a region which we call as boundary layer, in which the velocity increases from 0 to close to the free stream velocity. And on the downstream of the body, there is a flow separation and there is a region which is called as wake. So in this region also, so in the boundary layer in the wake region, the viscous effects are appreciable and the Bernoulli equation is not valid. So the approximation for Bernoulli's equation is, you can use Bernoulli's equation where viscous effects are negligible as compared to inertial, gravitational, and pressure effects. In fluid mechanics, we apply Newton's second law of motion, which says rate of change of momentum is equal to force. So when we talk of rate of change of momentum, the momentum change is considered as inertial effects or inertia force. And on the right hand side of the Newton's second law of motion, when we talk of forces, we have forces due to viscosity, which is called as viscous forces. We have forces due to pressure, which is called as pressure forces, and due to gravity, we have the gravitational forces. So among the various forces which is considered in fluid mechanics, note that in Bernoulli's equation, we consider, when we apply Bernoulli's equation, we apply in region where the viscous forces are or viscous effects are negligible. Bernoulli's equation can be derived from in two ways, by conservation of linear momentum and conservation of energy. Here the derivation will be presented from conservation of linear momentum. This Bernoulli's equation provides an approximate relation between the pressure, velocity, and elevation, which are called here as flow energy, kinetic energy, and potential energy. So just to give you an idea, when we study the fluid mechanics, we have these three here. Whenever there is a fluid flow, whenever we call this flow energy, what we mean is the energy due to whenever you have pressure and whenever there is a change in volume. In thermodynamics, you've studied the pressure multiplied by the change in the volume is a form of the energy that we call here as flow energy. So I will show you separately. So as I mentioned, the flow energy is basically given by pressure into change in volume. The kinetic energy is given by m u square by 2, and potential energy is given by mgz, where z is the elevation. Now if we write this in per unit mass basis, so whenever you have a pressure, when we say flow energy, we mean this PdV. When we talk of kinetic energy, we take the velocity of the fluid, and when we have a potential energy, we have the elevation. So this is presented in terms of expressions here. Now I will show you the derivation of the Bernoulli's equation from the when we will apply the linear momentum conservation. So when we apply the linear momentum conservation, basically we are applying the Newton's second law of motion. So we have to talk, then there we talk about the change of momentum is equals to the force. So now to calculate the change of momentum, basically in momentum is product of mass into acceleration. This Bernoulli's equation is applicable along a particular streamline. So here in this figure, there is a streamline which is shown, and we take this streamline. Since the Bernoulli's equation is applicable along a streamline, to derive it, we take a streamline whose direction is given by a coordinate which is called as s coordinate, and the normal direction is given by the r coordinate. So along this s coordinate, which is a tangential coordinate, acceleration is described along this any streamline by the distance s, which is tangential to a streamline, and the radius of curvature of this streamline. Now, so when you talk of the, let's suppose you consider the velocity along this s direction as u, then what you, so let us, so u is the velocity in the s direction. So if we talk of the variation of this velocity u, it's a function of the s coordinate and time. So you can express it as du is equals to del u by del u by del s into ds plus del u by del t of dt. Now if you divide this by dt, you can basically get acceleration in the s direction, which is du by dt. Now this du by dt, if you divide this by dt as shown here, then in this dt cancels down, and this ds by dt is equal to the u velocity. So you get del u by del t plus, now here you have, so here from here we have got del u by del t, and this term is given by u del u by del s, which is as shown here. However, when we apply Bernoulli's equation is applied for a steady flow. So when we consider the flow as steady, then this term is 0. This is 0 for steady flow. So the acceleration which is being presented here, the acceleration which is du by dt for a steady flow is equals to u del, what, there is a mistake here, this is del u by del s, u del u by del s. So this is also an s. So the acceleration for a steady flow in a Lagrangian system, I had mentioned it's a single term. This is del u by del t is equals to u del u by del s. So in a Lagrangian system, the acceleration is a single term, but in an Eulerian fixed position system, we have two terms, and in a steady flow, I had taken an example of flow through a nozzle in an earlier lecture, where I had mentioned that if you consider steady flow in a nozzle, that when you consider steady flow in a nozzle, the steady flow means this time derivative is equal to 0. However, in a nozzle, as the fluid is moving ahead, the velocity is increasing because nozzle is a decreasing cross-sectional area system. So you have an acceleration, which is due to the variation in space, variation of the velocity along the spatial directions. So to derive the Bernoulli's equation, we'll consider this. However, now since we are considering a steady flow, u is only function of s, not time. So we will write this as not as a partial derivative, but we will write this as total derivative. So the acceleration in a steady flow, there are two acceleration. Right now I showed you a derivation for the tangential acceleration u du by ds, where del u by del t is 0 due to steady flow as shown here. So this tangential acceleration is due to the change in the speed of a fluid particle when it is moving on a streamline. Note that on a streamline, the fluid particle moves tangentially and it cannot cross the streamline. So when fluid particle is moving along a streamline, if its velocity is changing, then due to the change in the speed, you have a tangential acceleration which is given here as u du by ds. But along with it, since there is a change in the direction, there is change in the curvature of the streamline, this leads to another acceleration which is given by the normal acceleration u square by r. This is 0 for particles that move in a straight path. So the steady flow that we are considering here is corresponding to an Eulerian, not for a Lagrangian system. And the steady flow which we say here means no change with time at a specified location, but the value may change from one location to other. So this specified location means del u by del t is equals to at a constant s is equals to 0. But you have del u by del s varying from, so when we say del u by del s, velocity is varying from one s to the other s. So it's a variation from velocity from one location to the other. So in the last slide, I had shown you the acceleration, the expression for acceleration in an Arrhenian system given as u du by ds. So now we'll consider that acceleration. And in this slide, the forces that are acting on a small fluid control volume, which we have considered along the streamline, is shown here. So the control volume which has been considered here is the length of the control volume is ds, which is along the streamline, and the cross-sectional area of this control volume is dA. So the total volume of this control volume is dA is the cross-sectional area, dA into ds. Now the forces that we are considering here are the inertia forces is given by the acceleration term. Other than the inertia, we have pressure force and the gravitational force. Pressure always acts compressive. So on this surface, the pressure that is acting is PdA. And as you move ahead, so you're basically moving from S to S plus ds. At S plus ds, you have P plus dP into dA. So if you apply the Newton second law of motion along the S direction, you get mass here, mass of the control volume is given by density into volume is given by ds into dA. So density into volume is your mass of the control volume. Mass into acceleration. Acceleration in the previous slide I have shown you, it is du by ds. This is on the left hand side, and on the right hand side you have forces. The force is PdA minus P plus dP dA. This is the pressure force. And other than this, you have a gravitational force. On this gravitational force, which is shown here as W, now W sine theta will be in the negative S direction. So we will take W sine theta, but it's a negative sign. Now this W is the weight, which is given by mass into acceleration due to gravity mg. Mass, we will write it as a product of density into volume of the control volume. So this weight is expressed as minus mg, where m is given by rho into ds into dA, density into volume, this is mass, and you have to multiply with the g, and you have a sine theta. Now, if you see the left hand side and right hand side, you can cancel certain terms. This dA is common to all the, on both left hand side and right hand side, so this cancels down. This ds is the numerator and denominator, it cancels down. This ds and sine theta. Now this ds sine theta, if you see here, ds sine theta is dz. So this is equal to dz. So if you now take all the terms on the left hand side, you can get an expression as shown here as dp by rho plus u du you will get, but that, okay, let me write down u du plus g into dz is equals to 0. Note that I have divided both the sides by density rho. That's why you have dp by rho. On the left hand side it is minus dp, you take it on the right hand side and divide by rho. So this is the equation which is obtained if you take all the terms from the right hand side to the left hand side and divide by the density. Now to get in finally the Bernoulli's equation, we will integrate this equation and obtain the final Bernoulli's equation. So when we integrate it, integral of dp by rho plus, now u du, you can write it as du square by 2 plus integral of g dz is equals to constant. Now, if the fluid is this, actually this is the second and third term are exact differential because g is constant, so you can take out of the integral, and integral of g dz you can write as dz, and integral of du square by 2 you can write it as u square by 2. However, in general, this rho in a fluid mechanics problem can be varying with space and time, which is we call as compressible flow. But however, for an incompressible flow, as the density is constant, then in that case you can integrate this. So then 1 by rho you can take it out of the integral, and then you can get p by rho plus u square by 2 plus gz is equals to constant. So for steady incompressible flow along a streamline, we have derived the Bernoulli's equation as shown here. Now, if you see this equation, you will realize that each term corresponds to an energy per unit mass. I will show you. This is mgz divided by mass. This is mu square by 2 divided by mass. This is, if you do p divided by rho into mass, rho into rho into mass, actually this is basically comes out with p dv, because when you divide by mass, this is pressure divided by density into mass, and this will finally this if you divide by mass, this is p dv divided by mass. Basically, when you P by rho is basically in pressure into volume divided by mass. So this is PdV is called as flow work. This is called as flow work. This you can express P by rho. You can express as product of pressure into volume divided by mass, because mass divided by volume gives you the density in the denominator. So this P by rho is basically corresponding to a flow work, flow energy, and this is kinetic energy, and this is your potential energy. However, each of these terms are energy per unit mass. This is the first form of Bernoulli's equation. I will show you two additional forms of the Bernoulli's equation. When I say a form, I mean what is the uh, unit, or what is the physical quantity that each term of the Bernoulli's equation represents. In this case, each term represents an energy per unit mass. So you can call that this form of the Bernoulli's equation is an energy form of the Bernoulli's equation. In the later slide, I will show you two more other forms of the Bernoulli's equation, which is called as pressure form and the head form. So as I said, that the energy form is the sum of flow energy, kinetic energy, potential energy of a fluid particle remains a constant along a streamline for an incompressible steady flow with negligible frictional effects. So the energy form, as I had mentioned earlier, is given by P by rho is plus U square by 2 plus Gz is equals to constant. Note that this constant in general varies from one streamline to another streamline. However, if the flow is irrotational, it has been shown that you can apply this, because if the flow is irrotational, then if you consider a different streamline, this constant is same. So you can apply the Bernoulli's equation between any 2 points in the flow region if it's an irrotational. So as I mentioned, when the flow is irrotational, as shown in this figure, you can see in this figure that, let us suppose there is a horizontal flow. So all the streamlines are shown by horizontal lines. So if you consider point 1 in this streamline and you consider another point 2 in the another streamline which is below that streamline, in this case the flow is irrotational, vorticity is 0 in this case. Then, and when the flow is irrotational, this Bernoulli's equation is applicable between any 2 points in the flow region, not just on the same streamline. After the energy form, the next form is basically P by rho, the earlier equation which I had shown. If you multiply all the terms by rho, because earlier we had P by rho. If I have to get pressure, I have to multiply by rho. So in this form, we get an equation which is P plus, earlier I had U square by 2, now I'm multiplying by rho, so I get rho U square by 2. Earlier I had Gz, now I will write it as rho Gz, this equals to constant. So this is the pressure form, where we call this as, this pressure we call as static pressure, this we call as dynamic pressure, and this we call as hydrostatic pressure. Now what is the static pressure and dynamic pressure? I will take an example problem. I will show you flow in a pipe, and we'll consider one piezometer uh, and which is used for measuring the static pressure, which is basically a vertical tube. And we'll also consider another measuring device which is called as pitot tube, which is used to obtain the combination of the static and dynamic pressure, which is called as stagnation pressure. So note that in this case, this is a pressure form of the Bernoulli's equation, where there are three pressure: static pressure, dynamic pressure, and hydrostatic pressure. So what are the differences between these three pressures? Static pressure is a thermodynamic pressure. So in thermodynamic tables, the pressure that is mentioned is the static pressure. And the dynamic pressure corresponds to a situation when the fluid that is moving is brought to rest isentropically. Then the pressure which is getting generated when the fluid which is moving is brought to rest isentropically, then that is called as the dynamic pressure. The hydrostatic pressure is, although the expression seems similar to rho gh that we have studied in fluid statics, here we have rho gz. But note that in the H that we consider in fluid statics, or the hydrostatic pressure that we consider in fluid static, it increases with depth. Now, in the rho g z that we are considering is corresponding to the potential energy, and the z we consider is the z increases in the upward direction. So this rho g z that we have in Bernoulli's equation, although it's not correct strictly to call this as hydrostatic pressure, this is not the same pressure that we have studied in the fluid statics. However, in pressure form, it is called as hydrostatic pressure. So these are the three pressures. And as I mentioned, to make you understand, this is an example problem which is shown here, where you have, let's suppose, flow in a pipe, where this is the velocity of the fluid, and this in this pipe there is a vertical tube which is attached to it. This is used for measuring the pressure and is called as piezometer. Along with it, there is another tube which is inserted. So this tube is passing through the, let us say, center line of the pipe. Now when a fluid comes in here, in this pipe, the fluid is stationary. So when the fluid is moving from far away, as it starts coming towards this fluid in the pipe, it slowly slows down, and here it stagnates. So this is called a stagnation point. It recognizes that there is a stationary fluid downstream, and it starts reducing its velocity, and its velocity becomes zero at this point. And after this point in this tube, the fluid is stationary. So this is like a stationary column of the fluid. So the fluid velocity is isentropically brought to rest here, and this leads to an increase in the pressure here. So here the pressure that is measured in this tube, what you measure is a static pressure. The pressure that you measure here, stagnation pressure, is E plus rho u square by 2. So here you see that the level of fluid rise in this pitot tube is larger, and so if the difference between the height of the liquid in a piezometer and pitot tube, which is shown by this arrow, the difference is corresponding to rho u square by 2, which corresponds to the dynamic pressure. In the tutorial video, I will take this problem and I will show you the derivation, that this is one of the common technique that is used to measure the velocity, where we have two measuring instruments, piezometer and pitot tube, and we take the difference of the height of the liquid column in the piezometer and the pitot tube, and we obtain the velocity. So this I'll take a tutorial video problem where I'll show you this expression and we'll solve a numerical problem. So as I mentioned, this piezometer measures the static pressure. The static pressure corresponds to a thermodynamic pressure. In the pitot tube, measures both static as well as dynamic pressures. Now the third form of the Bernoulli's equation, the first form where each term of the Bernoulli's equation is energy per unit mass. The second form where each term of the Bernoulli's equation is pressure. And the third form that is shown here is we want to express it in terms of head. Like in fluid statics, you have studied that pressure is given by rho g h. So if you want to convert it in terms of a dimension, height, then rho gh you have to p is equals to rho gh. But if you want to convert this in terms of head, then basically it's p by rho g is equals to h. So what we will do is that in the energy form we have P by rho. So if we divide that by G, so we'll get an equation which I will show you here. You will get, so the third form of the Bernoulli's equation is presented here as we are basically dividing by G. Earlier it was P by rho, now we have P by rho G plus U square by 2G plus we had Gz. Now when we divide by G, we are left with Z is equals to constant. This constant we are getting because on the, when we were deriving, we integrated, and although before integration it was 0, and we integrated and we got this constant on the right hand side. And for an irrotational flow, I had mentioned that this constant is same on all the streamlines. So if you consider the three different terms in this equation, you will see that this is the what is called as pressure head, this is called as kinetic head, and this is called as elevation head. Now we can draw certain lines for a particular problem. So let us consider this problem which is shown here. This corresponds to flow in a pipe. This is a pipe in which the fluid is flowing, but later on it has certain, now what is you are finding here is that the cross section of the pipe is getting reduced. So later on the downstream you have a pipe of small diameter. So the fluid is moving from a pipe of larger diameter to a smaller diameter, and then again from a smaller diameter it is coming to a pipe of a larger diameter. Now to connect the pipe of a larger diameter to a smaller diameter, we have a section which is what we call as nozzle, which is a reducing cross-sectional area. And on the other side, from the smaller cross-sectional area to the larger cross-sectional area, we have a system which is called as a diffuser, which corresponds to increasing cross-sectional area. So this is a problem with which I will discuss when we present the Bernoulli's equation in the head form. We commonly draw certain lines which are presented here as hydraulic grade line and energy grade line. And the hydraulic grade line basically consists of this pressure. Hydraulic grade line, let me show you. So this and this, the combination of these two is considered in hydraulic grade line. Whereas when we consider all these three, then we have energy grade line. Okay, now I will explain you how do we draw these lines through this example problem. So in this, what is shown is you have a piezometer as shown here, and you have a pitot tube. All of you know that this piezometer, what happens is basically the fluid which is near to the solid surface of the pipe. So it means that the fluid has zero velocity. The fluid which has a zero velocity near to the wall, the pressure of that fluid is measured here. This is called as a static pressure. Now the fluid, the pipe diameter is not large enough, so the elevation we can consider it to be constant. So Z is almost constant here, and this is corresponding to Z plus the static pressure. And then so from your hydraulic grade line starts from here, and your energy grade line, the difference between the energy grade line and hydraulic grade line is U square by 2G. Now if you take the average velocity of the fluid passing through this pipe and you consider that as the velocity U square by 2G, then above, so this is that, if I draw a dashed line from here, this is corresponding to the hydraulic grade line. And if I add V square by 2G, then I get another larger height, which I'll call as energy grade line. So here I'm showing you for this example problem. Let us suppose if I have this piezometer and this pitot tube, and I know the level, then with the help of this I'm showing you how do you draw the hydraulic grade line and energy grade line. So this hydraulic grade line is basically corresponding to consider the static pressure and the elevation. So in a pipe, note that while applying the Bernoulli's equation, we are assuming that the viscous resistance is negligible. So this energy grade line is shown as a horizontal grade line. In the next slide, I will show you that if you consider the viscous resistance, this along with this three term, there is a loss term, energy loss. And due to that energy loss, because when the fluid is flowing through the pipe, due to friction, there is a pressure drop that I'll consider in the next slide. But in this slide, let us say that there is no frictional effect near to the wall, and the pressure of the fluid which is moving through a constant cross-section area such as pipe, the pressure is remaining constant. So that way, the energy grade line and the energy grade line and the hydraulic grade line, when it is passing through a pipe of through a internal flow of constant cross section, you see that this is a larger pipe and this is a smaller pipe. Now, when you consider the hydraulic grade line and energy grade line for the larger pipe, for the length of the larger pipe, as well as for the length of the smaller pipe, you see it's horizontal. But when it is passing through this nozzle, what happens in a nozzle is the velocity increases, because if you consider incompressible flow and if you apply U1, A1 is equals to U2, A2. So when area is reducing, the average velocity is increasing. When the average velocity increases, but the pressure decreases. So since pressure is decreasing, the hydraulic grade line, it is moving downward. When pressure decreases, the static pressure decreases, the hydraulic grade line moves downward. However, note that the decrease in pressure is compensated by the increase in the velocity. So the gap increases between the hydraulic grade line and the energy grade line because the velocity is increasing. So, and then when it is passing through a pipe of smaller cross section, then again it remains horizontal. When it is passing through a diffuser as shown here, now when fluid passes through a diffuser, the velocity decreases but the pressure increases. So since the pressure is increasing, the hydraulic grade line moves upward, and when it is finally passing through a pipe of a larger diameter, it remains horizontal. Because here we are considering negligible frictional effects. So the pressure when it is flowing through a pipe, it is not reducing. So this way, for the flow in a pipe with a nozzle and a diffuser, taking a piezometer and pitot tube, the pressure, basically we are considering the pressure variation due to change in the pressure and velocity variation due to the change in the cross-sectional area. We are not considering the pressure variation due to the frictional effects. And I have shown you that these are the lines, because basically these are certain heights, and those heights we obtain by this expression. If you consider the height due to the static pressure and the elevation, then we get a height which we are denoting here as hydraulic grade line, where when it is passing through the nozzle, the pressure is reducing. So this hydraulic grade line is moving downward. Later on, when it's passing through a diffuser, the pressure is increasing, so it's moving upward. But finally, for the larger pipe, before it is passing the nozzle and after it is passed through diffuser, the horizontal line before and after remains same. Whereas this energy grade line, you always see, because basically it's a combination of these three, and here we do not have any loss term, so this is horizontal. So the total head, so this we call as pressure head, this we call as kinetic head, this we call as elevation head. And the summation of these three we call as total head. Energy grade line represent total head, whereas this hydraulic grade line represent the pressure and the elevation head. So as I mentioned here, this in Bernoulli's equation, energy grade line is horizontal. Otherwise, it has a downward slope due to energy loss. What is mean by this is that in this pipe, when you consider actual situation, due to the viscosity of the fluid near to the solid wall, there is a velocity gradient which leads to the decrease of the pressure of the fluid when it's passing through pipe of constant cross-section area. So, but if you neglect that, energy grade line is horizontal as shown here. Otherwise, it has a downward slope due to energy loss that I will show you in the next slide, where I will consider the frictional losses. So if you consider an ideal Bernoulli's equation where frictional losses are negligible, then you have energy grade line as horizontal. But while you are applying the Bernoulli's equation and when you are considering the So in an ideal Bernoulli equation, this is horizontal. But if you consider practical Bernoulli equation, then other than this three term, you have additional loss term. And that due to that loss, this energy grid line will have a downward trend, which I'll show you in the next slide. So here I'm showing a similar problem. Well, let us suppose there is a fluid in a tank and the fluid is coming out to a pipe of a smaller diameter. Then it is finally getting out from a pipe of a larger diameter. Now to connect a pipe of a smaller diameter to a larger diameter, there is a diffuser which is used, which is shown here, which is corresponding to an increasing cross-sectional area. And you know that, as I mentioned, that when the cross-sectional area is increasing, the average velocity will reduce, and velocity reduces, but the pressure increases. So in this case, even though when the fluid is passing through a pipe of constant cross-sectional area, you will see what is shown here is this solid line is corresponding to the energy grid line, and this dashed line is corresponding to the hydraulic grid line. Now, what you see here is even when it is passing through this constant smaller pipe diameter or a larger pipe diameter, in this region also the total energy grid line, it's shown with a downward slope. Here also there is a downward slope. Now, as you can see, but the slope is the slope is constant. Assuming that the flow has become fully developed and the frictional resistance is per unit length is same, then in that case you can have the slope downward slope as constant. And so practically, if you have many, in earlier slide I have shown you only one piezometer and pitot tube. Here in this, if you can see in the practical situation, even though this is a pipe of a constant diameter, at two locations, if you have a piezometer, at upstream location and a downstream location, what you see is the static pressure measured in the upstream location is larger, and in the downstream location, the pressure has reduced. So when the fluid is passing through this smaller pipe diameter, the static pressure that you measure from the piezometer is reducing. Similarly, when you consider the larger pipe diameter, if you consider three locations, let us say this location as x1, this as x2, this is x3. So if you consider static pressure as P1, P2, and P3. So the pressure that you measure, P1 is greater than P2 is greater than P3. So the pressure, the static pressure in practical situation, the static pressure is reducing. So if you use Bernoulli's equation for actual situation, along with those three head term, there is a loss term which corresponds to the energy grid line. And so considering that, in this case, these lines are having a downward slope even if it is passing through a pipe of constant cross section. And now, as far as the distance between this hydraulic grid line and this, when it is passing through a pipe, the velocity is, note that when the fluid is leaving this tank and entering into a pipe, there is a cross section which is being, so you can see that this is like a nozzle. This is like gradually the cross sectional area is reducing. So since this is a nozzle, the velocity increases and the pressure reduces. So there is some inlet effect which is being predicted here. Now in this pipe of a constant cross section, the difference, you can see that the gap between these two lines, when it is passing through this pipe of smaller diameter, the gap is constant. So basically it is corresponding to the average velocity of the fluid in the pipe, u1 square divided by 2g. Here also you can see when it is passing through a pipe of a larger diameter, the gap between these two lines is constant, and it corresponds to the average velocity of the fluid on the larger pipe, which is, let us say, u2. So this is u2 square by 2g. Whereas when it is passing through this diffuser, you should know that when it is passing through the diffuser, the static pressure is increasing. So this hydraulic grid line, which consists of combination of the static pressure and the elevation. The elevation that we consider in this problem is corresponding to the center line passing through this pipe, and that elevation is same along the axial direction. What is varying is when it is passing through diffuser, the static pressure will increase, the velocity will reduce, but the static pressure will increase. So the gap between these two lines will reduce. So the energy grid line and hydraulic grid line approach each other, or the gap between these two lines reduces, As the velocity decreases, and when the velocity decreases, what is meant by is the static pressure increases, okay, and vice versa. So, such as in this case of nozzle, the velocity is increasing, but the pressure is decreasing in this case. So this is a hydraulic grid line and the energy grid line that is presented when you consider the frictional losses. And for a stationary fluid, you don't have any velocity. So the energy grid line and the hydraulic grid line coincide at the free surface. So I had shown you three different forms of the Bernoulli's equation: the energy form, the then this is the final form which I have shown corresponding to the head, and I have also shown corresponding to the dynamic pressure form, where we have shown it like the static pressure, dynamic pressure, and the hydrostatic pressure. I would again like to repeat that when you present the pressure form of the equation, the hydrostatic pressure here that we represent rho g z is corresponding to the potential energy, and the z that we consider increases upward. So this hydrostatic pressure rho g z that we are considering by Bernoulli's equation, this increases with high as you move upward, whereas the hydrostatic pressure that we consider in fluid statics, as you move upward, when you consider this rho g h, the pressure was reducing when you moved upward. This I had come to the end of this lecture. These are some of the references corresponding to this topic. Thank you for your attention.